start off here talking about some basic exponent rules from algebra. Product of powers, if they have the same base, both of these are base x. Product means you're multiplying. You should add the exponents together. So x squared times x cubed is x to the 5th. Or as I have over here, x to the 8th times x to the 11th is x to the 19th. Product of powers with the same base, add their exponents. Power to a power, you multiply the exponent, so x squared cubed, 2 times 3 is 6. X to the 5th squared is x to the 10th, because you multiply the exponents. A quotient of powers, quotient means you've got a fraction right here. You're really supposed to subtract the exponents. I've always played where are there more game. You've got 5x's upstairs and 2x's downstairs. Don't you have 3 more x's upstairs? So you got x to the 3rd over 1, if you will, because there's more upstairs. Here, y to the 4th over y to the 7th. There are more x's downstairs, so that's why they stay down there. The real rule says subtract, you'd get y to the negative 3rd, but you're not allowed to have negative exponents, which means you should reciprocate the base, and you get this. So just play where are there more, upstairs or downstairs. So let's do that to this guy right here. There's x's and y's. X's, there's 1 more downstairs, because there's 3 down there, and there's 2 up here. Y's, there's 1 more upstairs, so that's what that would simplify to. Negative exponent, as just mentioned earlier, means you should reciprocate the base first. So this is really, reciprocate means flip it over, 3 halves. Then you take it to the first power, which is still 3 halves. Over here, you have a negative exponent, so you should reciprocate the base first, and now it will be to the positive second power. That's all that negative exponent meant, was reciprocate the base. Now you square each guy and get 16/9 for this guy. It says rewrite this with a positive exponent. So first I'm going to go ahead and call it 13 to the negative 8th because it's a power to a power. Then this guy needs to change houses. He's really upstairs. So it would mean that the 13 to the negative 8 becomes down to the denominator. It becomes positive, and there's a 1 in the numerator. My math lab might let you type it in like this, or if you put 13 to the 8 in your calculator, you'd get 1 over this big old honker number of 815730772. Move over. My bad. Is that it? 721. Go back and put commas. Blow. Blow. So that's a big mega number right there. Multiplying polynomials, if you take a binomial times a binomial, you need to FOIL that, which means you need to take your first terms times each other and get x squared, the first term in each parentheses. Your outside terms times each other, here you get minus 3x, because x times negative 3. Your inside terms times each other, and you get 1x. And then your last terms times each other, first, outside, inside, last. Then you should combine like terms, if you have any. And here's our final answer. Binomial squared. Over here, a special shortcut is if you had a, my bad, I said binomial squared, but it was a binomial times a binomial. If you have a binomial squared, you know, it means you're taking 2x plus 5 times 2x plus 5, but there's a shortcut that'll end up happening. The middle two terms will always end up being the same. So like if I did FOIL it, I'd get, with the right math, 4x squared plus 10x plus 10x plus 25. But notice those middle terms are always the same thing. So that's why we say we have twice the product of those. First thing, here's the shortcut. Number 1, square the first term. So 7x squared would become 49x squared. Then take twice the product of these two terms. First you got to figure out what the product is. The product is negative 14x. Twice that is negative 28x. And then you square the last term and you get 4. And that's the shortcut to a binomial squared, because those middle terms are always the same. So if we square the first term, this would be 16x squared. Twice the product is 8x. Twice that is 16x. And then square the last term, you'd get a 4. And you might note for later purposes that these are called perfect square trinomials right here. That's when you had a binomial squared, the same thing times itself. Conjugates is like where they almost look the same except for the sign. It's the exact same thing in the parentheses except for the sign. And what happens if you were to FOIL it out, you'd get a squared minus ab plus ab minus b squared. the middle terms, the outside and the inside, always add up to be nothing. So during the FOIL process, all you have to do is take the first terms times each other and the last terms times each other when they are conjugates. First terms times each other, 4x squared. Last terms times each other, negative 25. That's it, because you would have canceled out with the outside and the insides. So these are conjugates. First terms times each other, 144x squared. Last terms times each other, 49, and it's negative. Notice these are what you call difference of squares right here. They are a difference of two perfect squares. Maybe, did I skip too much? Yep. Absolute value is how far the number A is from 0 on the number line. So for example, if you had a number line, here's 0, and if you had 5 on there, isn't 5 units away? So they call it the absolute value of 5, which is 5. Even if you are at negative 5, isn't that really 5 units away? So absolute value of negative 5 turns out to be 5. You've always been taught that absolute value means take what's inside and make it positive. Well, of course it is a grouping symbol first, so if there's anything to do inside the absolute value bars, you need to do that first. Here this is just 3. Absolute value of 3 is 3. Nothing to do inside here. Absolute value of negative 23 is 23. There is stuff to do in here. You've got the absolute value of 2 minus 4. Well, 2 minus 4 is really negative 2. So you need to do what's in the grouping symbols first. Then absolute value of negative 2 is a positive 2. Rational exponents, you'll see them written like this. You know, you have your base of x, and it's to the power over root. It can also be written with a radical. This guy right here on your little shelf called your index is the root, and the guy underneath here is the power. So they ask you to rewrite this with a rational exponent. This is a root. This is the power right here. So your base is still x, and if it's power over root, that's x to the 2/5 power. To rewrite this as a radical, since this is power over root, your base is still x. You're going to have a radical around it. Power goes in here. Root goes right there. Power over root. Just remember that phrase. Power over the root. Factoring. Yay! First kind of factoring is called the greatest common factor, where every term has a common factor in it. You see this term and this term, they both have a common factor number-wise of 5. 5 is the smallest number that goes into both of them, and each one of them has an x. So we take out the smallest amount of x's, and that's x to the first power. We're like undistributing, if you will. Then if you was to take this guy divided by this guy, 5 divided by 5 is 1. X squared divided by x is x. Or if you could think of it, 5x times what would give you 5x squared. Minus. Then you divide 10x divided by 5x, 2. And x's cancel each other out. We just undistributed a 5x, taking out the GCF. So let's do that to this one. Just go one thing at a time. Look at the numbers. Between a 4 and an 18, I can take out a 2. Between the x's, each guy does have an x in it. Take out the smaller amount, which is x to the first. And between the y's, take out the smaller amount, but as large as you can possibly take out, we can take out a y cubed. Now if I divide, 4 divided by 2 is 2. X squared divided by x is x. Y cubed divided by y cubed cancel each other out to be 1. Here comes the subtraction sign. Then divide again. 18 divided by 2 is 9. X divided by x is 1, so it's gone. And y to the fourth divided by y to the third is y to the first. I just took out the GCF in each one of those problems. These don't have GCFs. They could, you know, you got to check to see if they got a GCF first. But if 1's the GCF, then you really say that that doesn't have a GCF. But these trinomials right here, they're what we call easily factorable because the a value is 1. If the a value is 1, remember your standard quadratic is ax squared plus bx plus c. If the a value is 1, all we have to do is find two numbers that multiply together to be c, that's him, and add together to be b. That's him. So, in this one, a is 1. Notice, it's not an equation. So we do not need to solve this. We just need to factor it. Unfoil it, if you will. Two numbers that multiply together to be 6, add together to be 5. I know you've done this many times, but the idea is you should talk yourself through what should be true about the two numbers. Should they both be positive, both be negative, or one be negative? When this c number right here is positive, both signs have to be the same. because a positive times a positive is a positive, and a negative times a negative is a positive. So I know the signs have to be the same. When this is the case, look to him. He will tell you if they should both be positive or both be negative. Since he is positive, these numbers should both be negative. So multiples of 6 that are both positive, 1 and 6, but they add to be 7, not our numbers. 2 and 3, they multiply together to be 6 and add together to be 5. So what we do is we set up two generic ordered pairs right here, like you're foiling. Whatever variable we are using leads off. Since that's a positive 2, I will put a positive 2 right there. Since that's a positive 3, I will put a positive 3 right there. And realize you don't need to solve this because you cannot, because it's not an equation. The only thing you can solve is an equation. If this equals 0, we have more work to do. But it's not equal to anything. A value is 1 right here. Find two numbers that multiply together to be a negative 12. That means that the two numbers have to be different signs. One positive, one negative. So multiply together to be negative 12. Add together to be a positive 1. So 1 and 12 don't work if one of them was negative. 2 and 6, if one of them was negative, they wouldn't add up to be a 1. A 3 and 4, ha-ha! If this one was negative and that was positive, wouldn't these two numbers multiply together to be a negative 12 and add together to be a a positive 1? So we factor it into this. Since the number we found of 3 was negative, we'll put a minus right there, and that's a positive 4, so right there. And again, we cannot solve him due to the fact that it's not an equation. Find two numbers that multiply together to be a positive 20. So since this is positive, both signs have to be the same, either both positive or both negative in the two numbers that we find. Look to him. He will tell you that they both need to be negative. So two numbers that multiply together to be a positive 20 add together to be a negative 9. 1 and 20 both have to be negative, no dice. 2 and 10 both have to be negative, no dice. 3 does not go into 20. 4 and 5 both negative. Bingo! Ding, 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 ding. X minus 4, x minus 5. Do not need to solve him, because he is not an equation. Alright, now time to slow down, Mr. P. Factoring when a is not 1. I call it frowny face factoring. 1, because it's not very much fun, and 2, because I make a little frowny face. What you have to do is take a times c. Hey, I missed. Take a times c. Put that number right there, and find two numbers that multiply together to be this, but add together to be b. Again, not equations, so we just need to factor it, but I ask you to please put the little frowny face right there, and see that those two numbers multiply together to be negative 50. Since they have to multiply together to be a negative 50, we need to find two numbers that are different signs, and they should add together to be 23. So we can try 1 and 50, and one of them had to be negative, but those add together to be 49 or negative 49, then 2 and 25, and if one of them was negative, which one of them is supposed to be, hey, right there, there's our numbers. So finding the two numbers is the first part. Then you have to split this guy up into 4 terms. Whoever is the first term, he always leads off. Then these two guys, you will put their numbers with an X with them. My advice is if one of them is negative, lead off with the negative one. It doesn't have to be in this order, but you'll see here in a second that it's better if you put the negative one first and the positive one second, and then the fourth term is whoever our last guy was here. All we have done is taken this 23x and split him up into a negative 2x plus a 25x. What we will do now is we will double group. The first two terms become a group, and the last two terms become a group. And now we will take the GCF out of each group. Between a 10 and a 2, the biggest number I could take out is a 2, and they each have an x in it, so I will take the smallest amount of x's out that I can, which is x to the first. And now I divide. I would get 5x minus 1 as a quantity in there. Then I do that process all over again, take out a GCF of each one. Whatever sign this is the type of GCF you will take out, so you must take out a positive, and 5 goes into each one of those. But x is not part of the GCF because there's no x in this guy. So once dividing, you will get 5x minus 1. And the way you know you factored by grouping correctly, aka frowny face, is these two groups must be the same. Now we could factor out a 5x minus 1 from each one of these two groups to where I've always said make your GCFs a group of their own. That's these two guys. Highlighter. That's these two guys. They become a group of their own, and that common group with a pen. Try again. 5x minus 1 comes down. That's just how to factor it. It was not an equation, so you don't need to solve, but we just unfoiled it. If you were to foil that back out, you should get a this. So let's do that again. Let's frowny face factor. The reason why we're doing it is because the a value is not 1. So multiply those together, get a negative 6. Find two numbers that multiply together to be negative 6 and add together to be a negative 5. One of the numbers has to be negative, so 1 and 6, but if one of them was negative, bobbing, that'd be these two. 4 terms. First guy, he leads off. These two, it really doesn't matter what order you put them in. If one of those numbers is negative, I like to put him first. Then last guy, minus 2. 4 terms. Double group. Take out a GCF from each group. I can take out a 3x. In my first guy, I would get x minus 2. You always have to take a GCF out. Whatever sign this is the type of GCF, so you'll take out a positive GCF, and there is no GCF between these. Well, there's always one. It's a 1 in this case, because you're trying to get an x minus 2. Well, it is an x minus 2, so 1 is the GCF that you're taking out of that group. GCFs become a group of their own. That's him and him. Common group comes down for the ride. No, it does not matter if those are in a different order. I do not need to solve this because it's not an equation. And finally, our refresher of complex numbers. A plus bi, where a is the real part and bi is the imaginary part. They will ask you, is the number that is in these problems here, is it just a real number, is it just an imaginary number, or is it a pure imaginary number? Well, a plus bi is a real number if the b value equals 0. That means you've got a 0 right here, meaning that doesn't exist because you had 0 times I, which is nothing. It's just a real number if there's no i's with it. It is an imaginary number if b is not equal to 0. So you have both parts. Let's make up numbers like 5 plus 2i. I have a real part and I have an imaginary part, so that's called an imaginary number. And it's called a pure imaginary number if a is equal to 0, meaning you've got no real part, and b is not equal to 0, so you do have an imaginary part, like 6i. Notice there was no real number, but there was an imaginary part, so that's a pure imaginary number. Then, of course, we've got the difficult powers of I. Let's define what I was again. Remember, I is the square root of negative 1. So when we did our powers of I to the first was just plain old I squared is really square root of negative 1 squared, and the square and the square root cancel each other out. So I squared is really the number negative 1. And then I cubed is the same thing as I squared times I. Well, since I squared we just said was negative 1, you've got negative 1 times I, so I cubed can be simplified down to be negative I. And finally, I to the fourth is like I squared times I squared, which is really like negative 1 times negative 1, which of course is a positive 1. Yippity-doo-dah. If you need help with these powers of I, let me know, and I will help you. Now let's go through these problems. They are saying identify if it is real, imaginary, or pure imaginary. So this guy, 6 plus 4i, he's got a real part, he's got an imaginary part. That is, just like this guy right here, he is an imaginary number. We can do a little bit of simplifying in our next one. You've got 3i minus the square root of 4, which of course is 2, and then we usually write it the other way around. It's a negative 2 plus 3i. He's got a real part, he's got an imaginary part, so he's an imaginary number as well. Oh no, we've got an I squared in there. I squared again, remember, is negative 1, so this is basically 3 minus 2 times negative 1, because that's what I squared is. That's the same thing as 3 plus 2, which of course is 5. That's a real part. There are no imaginary parts. So, since there's no imaginary parts, that's just a plain old real number. It's so real that it magically turned red instead of blue. Green, please. This guy, we can clean him up since there's a negative number underneath the radical. When that number, even though it's negative, is a perfect square, like 16 is a perfect square, it's pretty simple. You just square root it and put an I with it. So you have your 4 minus, and then this square root of negative 16 becomes 4i, because it's really the square root of negative 1. Let's write it out a little better, please. The square root of negative 1 times the square root of 16. Here's your 4. Here's your I. When you're multiplying together, it's 4i. It's got a real part. It's got an imaginary part. So that, my friends, is an imaginary number. And then this guy, it's a negative underneath the radical. But 3 is not a perfect square, so it's really this. It's negative 1 times, square root of negative 1 times the square root of 3. This is really I square roots of 3 is what he simplifies to. So that is a pure imaginary number because there's no real parts with it at all. So I square roots of 3 is what he is. Awesome.